I'm recording this particular lecture so that in case if you want to hear later. But anyways, I had to again come back home, and that is the reason I'm presenting it online today. So we will start with AES. I'll quickly run one specific video so that you can see. I think you are able to see. One second. I'll do one more time. Okay. So does anyone remember what was in DES? We covered S-box substitution. Do you guys remember what exactly it was? Anyone? Where I asked you some couple of things. Does anyone remember? This part, S-box?
Yes.
Okay. So here, generally in S-box or DES, there are two kind of very important property. And if you recall, there were two properties were confusion and diffusion, that if a single bit change happens in the key, that it would change the entire your ciphertext. So if a single bit, if your bit is 001, it will change your nearly half of your ciphertext completely. So if you are using 1001, and next time if you use 1000, just a single bit would change the entire thing. So avalanche effect in DES is small change in plain text or key should create a significant change in the ciphertext. And the other important property is that the ciphertext, whatever ciphertext is created, it depends on many bits of your plain text. And the underlying assumption is that we use this S-box substitution, which is already defined, and the sender and the receiver just use that S-box which they have already created. The issue with that S-box substitution was that you have to both the sender and the receiver have to decide that S-box numbers initially, and it becomes a little bit cumbersome in order to come up with these numbers. And that is the reason AES came into a picture where instead of these predefined S-box value, they create the S-box values by themselves. And in order to create those S-box value, they use this concept of Galois field to generate the numbers which are substituted in this S-box. The rest of the mechanism is very similar, that you start with your initial plain text, you process. The only difference is that in your the number of bits which are being processed in AES is also much larger in comparison to your DES. So DES used a 64-bit. This AES can be used for 128 bits, 192 bits, and 256 bits. If you are processing 128 bits together, then the number of rounds are limited to 10. If you are processing 192 bits, then the number of rounds are 12. And when you are processing 256 bits, then the number of rounds is 14. In comparison to DES, if you recall, DES required 16 rounds, and every time 64 bits are processed. But in AES, this is variable. You can process 128 bits, you can process 192 bits, you can process 256 bits. And the number of rounds are dependent on the number of bits that you are being processed. The other thing that that is very important in this is that if you recall in your DES, the fistal cipher structure was predominantly being utilized, where you shuffle these bits together, you expand the bits, you perform this S-box, and then you again switch your left-hand side and right-hand side. These things doesn't happen very predominantly. You do not divide the bits. However, there is still a kind of fistal nature in this specific advanced encryption standard. So that you will be able to understand once I run that animation. And it's a good animation tool. You can, if you want to understand any of the other cryptographic puzzles, you can always go to that site, and that site allows you to have certain kind of animations that would help you to understand rather than these slides that are present. But anyways, so in each round, what happens is that each round comprises of four specific modules. One is substitute byte, second is shift row, third one is mix columns, and the fourth one is add round key. And I'll tell you what happens in each one of them, but each round comprises of four of these specific modules. The only difference is that in the last round, we do not have mix columns. This specific module is missing. Otherwise, rest of the rounds are clearly, it's exactly the same. So you substitute the bytes, you shift the row, you apply mixed columns, and you do the add round key. If I come back to this specific diagram, you will see that here we are processing 128 bits, which means that the number of rounds would be 10. And here, initially, the key is also expanded. So you start with 128-bit key, but if you want, when you start this 128-bit key, every time a new key is created for each of these rounds. You cannot use the same key that you are using in each of these rounds. And that is the reason they perform a key expansion. They start with 128-bit and then they expand it for each round by reusing the previous bits that they started with, but with certain kind of modification. And that is the reason it's showed as the key expansion. At the end, you will get 128-bit of ciphertext, or you can get 192 based on the number of bits that you are processing. Also, one important aspect in AES encryption is that you process it in the form of words. And since I mentioned it is 128 bits, so you arrange the number of bits in this table, or you will say a 4x4 matrix. So here it would be something like this, where you will have these bits, and each of this first row will comprise of 32 bits. So these are, this word is basically 32 bits. This is 32 bits. So this is one word. This is another word. And this is your third word. And this is your fourth word. So every process that happens is on the word level, which means 32 bits are processed. Remember that 32 bits are processed, which means words are being processed. In the other case, in the DES, you had divided into two parts, which was 32 and 32. You were not processing in the form of word, but here you have your matrix designed in this 4x4 matrix, and you process word by word. And in each of these round, you will have substitute bytes, shift row, mix column, and add round key. And this is the S box, which is being used. Similar to your DES, we had our S box. In AES also, we have this S box substitution, but rather than predefined values, as I mentioned, these values, which is 054F91DB2C, these are being generated using this concept of Galois field. I'll not be covering this because it's a little bit in depth to make you understand how exactly these S box values are being created. But I'm offering this cryptography course next semester for those of you who are interested to understand in details. And if you're enjoying cryptography, I would encourage you to sign up for that specific class so that you can understand more in depth some of these concepts. And you will also write certain codes to understand all of this mechanism. This course that I'm offering is 4379H if cryptography, and it's offered in your fall 2025 if you want to understand more on cryptography and other puzzles. So circling back, that as I mentioned, that each of the round comprises of 4 specific modules. One is steps substitute bytes. Here, what you will do, as I mentioned, that you process it in a word. So this is your word number 1. This is word 2. This is word 3 and word 4. So what you will do is you will look at these numbers, which is, and each of this is 32 bits, and each of this part is 8-bit. So for this, you will look at these 8 bits and you will go back to your S box, which you have created, and identify the position to substitute the value. So for instance, if your bit is 45, then in that case, 4 would be written in binary, 5 would be written in binary, and then you will look at the S box and you will identify that specific position and you will substitute it to that corresponding new block. So this first 4 bits generally tell you the row and the last 4 bits tell you the column. So if it is 4 and then 5, so 4 would be substituted in its binary equivalent, 5 would be substituted in its binary equivalent. So first 4 bits will tell you the row and the last 4 will tell you the column. And in that case, you will go to SBox and you will identify that specific position. That is substitute bytes. The second one is shifting the rows, where you shift the word. So here in the first word, you do not make any change. In the second word, what you do is you shift one bit. So one of the bit would be shifted. One bit would be shifted. So if it is 10110010, it would be 0110010. And this one will come to the last bit like this. The second one is 2 shifts, which means 2 times this bits would be shifted. And in the third row, 3 times the shifting would be done. And finally, you will get some new matrix. That is shifting the rows operation. The third one is mixing the column. Here you will take each of these words. This time you will take it in a column and you will multiply it with a constant matrix. And then finally, you will get a new matrix. That is mixing the column. The last one is adding the round key. And here is when you will take your previous output that you got by mixing the column. And then you will take your round key that was also 128 bits, which means that it is also arranged in this word format. And you will apply an XOR operation on these bits. And finally, you will get a new output. So in each of these rounds, 4 of these operations happen. Substitute bytes, shift row, mix column, and add round key. And in the last one, this doesn't happen. So I believe this has given you enough understanding on what exactly happens in AES. Now I will run that animation so that you can see a live demo. Let me go over here. I think you're able to see this part. So this is a crypto tool online. If you want to just search crypto tool, AES animation, or just go to this website called Cryptool, you will have multiple of these ciphers and some of the codes which are available. What is crypto analysis and other thing, but they have also very good animations. They also have source codes for some of the algorithms that you implement, but it's a very good website. So in order for you to understand this AES, I'll start this animation so that you can take a look. So here it is. So as that these words are arranged. So first block goes to the encryption process and the keys goes to the key expansion. So first they are explaining the encryption process. So these are the 4 rounds that I just explained. This happens 9 times. And finally, in the 10th round, we do not have mixed column. So first is that substitute bytes. So they take these 8 bits together and go to that S box and pick that specific number to substitute its corresponding value back to the original matrix. This is shift row operation where they shift or rotate these over 2 bytes. And this is three bytes rotation. Now is mixing column, where they mix it with your constant matrix, which is also been created by Galois field. Then is the round key. They take one column, add a round key to generate a new column. Finally, they get the output, which is also 128 bits. So this is encryption process. Now they will show you how exactly the keys are expanded. So they have this mechanism where they rotate the words using the S box. So what they do is, for instance, if they decided initially 128 bit of the keys, so what they do is they look at the S box to come up with a new value, which they get it from the S box that they create initially. Then they substitute with the first column, apply an archon, and they get new 32 bits. And this process is repeated till you process your entire 128 bits. There is another process to even get this archon. And once again, we are not understanding all of this. The main reason I wanted to show this so that you understand the difference between AES and DES. There are 2 major differences. DES processes 64-bit, AES processes 128, 256, and so on. The other important difference is that DES creates the S box initially based on some random values. However, the S box in AES uses Galois field to create the S box. And third important thing which is different is the fiscal cipher structure, which is being maintained in the DES. In AES, it's different. They do perform some kind of rotation and other thing, but primarily they do not use the fiscal cipher structure that we covered last time. They use these substitute bytes, shift row, mix columns, and add round key. So these are the 2 standards which are important in cryptography. If you want to understand more on any of these, as I mentioned, Cryptool is one good website so that you can go through the animation to understand it. But you will see that DES was developed in 1977, but then somebody was out there as a malicious hacker who even made the DES fail. And that is the reason advanced encryption standard came into picture. But in between also, this DES and AES, also there was a time that people also came up with triple DES. So what they did is that, remember that DES was so complicated. We understood that we process the 64 bits, we apply a key, we follow this fiscal cipher structure, and finally we get a 64-bit ciphertext. And there are 16 rounds which are happening in our DES. But people were not satisfied, and somebody was out there who could hack into this DES mechanism. So they came up with triple DES, where what they did was, the only difference is that they applied the 16 rounds 3 times. So you start with your ciphertext, which is, plain text, which is your 64 bits. You go through that fiscal cipher structure 16 times. You get a 64-bit ciphertext. You again process it back into another DES. So this was your first. Then you take another DES block, where the only difference was the key that you utilized in the first one was different in the second 16 rounds that you are processing. Then after that, you again get 64-bit of ciphertext and you reapply your DES. And finally, that after that, once you get that output, that became your ciphertext. So it applied this triple DES, and you remember that the complexity of a single DES was so complex that applying triple DES is way too much. So in between this DES and AES, there was also this triple DES. And if somehow any one of you want to try, you can come up with 5 times DES, 10 times DES. But the AES was considered much more secure in comparison to DES. The key length in DES is 56-bit. In AES, as I mentioned, you can process 128, 192, or 256. It is symmetric. This is also symmetric. Block size is 64-bit. AES can capture 128-bit, 192-bit, or 256. This is considered less reliable in comparison to AES. So these are the primarily major differences between AES and DES. Any questions so far? Good. Okay, so no question. So we will now cover Stream Cipher. So Stream Cipher is a kind of a bit-by-bit operation. So far, we did understand like monoalphabetic, where we took a single letter and then we substitute certain values. We also processed a couple of letters together, and for that we used Playfair cipher, Hill cipher, and we also understood standards which were AES and DES. And Stream Cipher, the only difference is that it does have a kind of bit-by-bit operation. So under substitution cipher, we did cover rod 13. For monoalphabetic, for polyalphabetic, we covered Wigner cipher, Verman cipher. For shift cipher, we covered Caesar. For transposition, we covered transposition cipher, columnar cipher, rail-fence cipher. For block ciphers, we covered Playfair, Hill cipher, DES, and AES. Now we will basically cover our Stream cipher, which is also a kind of an encryption algorithm. Here, the only difference is that you process bit by bit and you perform an XOR operation to get your resultant. Once again, XOR is represented in this format, and you process bit by bit to get your ciphertext. The major question comes over here in Stream Cipher is, how do you generate a key which is so much pseudo-random that nobody would be able to decipher it? because the problem is that when you send multiple or single bits together and you perform an XOR operation, and let's suppose this is your key and you have 1101, how exactly this, how can you make this key random in nature that nobody would be able to understand what were the bit values? And that's what we will cover in Stream Cipher. So Stream Cipher, if you recalled, I had shown this kind of animation where you repetitively repeat the key value so that you will process one bit together, perform an XOR operation, and you will get your ciphertext. The ciphertext is not dependent on this, but it is just for your understanding that you process one bit together and you will get a ciphertext. We will understand how to create this key stream so that it is random in nature. So how many of you have heard about a linear feedback shift register? Anyone? LFSR.
I think we did that in our computer architecture.
You did? Okay.
It sounds familiar, but I don't really actually know what it means.
Okay. So a linear, yeah, go ahead.
No, I just said same here. Same as what Brandon said.
Yeah, so what it does is that it has some kind of, it's a linear in nature, which means you have some polynomial function, which is linear in nature, and it also performs some kind of shifting. And there is a feedback. That is the reason it is called as linear feedback shift register. So this particular concept was used to create keys for your LFSR, for your stream cipher. And we will understand how exactly this happens. So for this, the only basic understanding that you should remember that a basic concept of a linear feedback shift register is that it arranges all the polynomial function in a linear, and then there is a flip-flop which trigger that specific coefficient to trigger a specific value. And I will make you understand this specific concept. But in the end, you apply a kind of a feedback where which specific flip-flop would trigger the next input value for this function. And for this, what you do is, for you to understand this specific concept, let's understand this particular concept using this umbrella mechanism. So let us imagine, just imagine that we have like 4 people in a group, and we have a girl. No, let's make this as a woman. This is as a man, and this is an old man, and this is a girl. So we have 4 people, and we are deciding that who has umbrella on a specific day. And initially, we start with some kind of random value. And let us suppose that random is that initially everyone has umbrella. And that is why we are depicting it by 1111. The consecutive day, the other individual will have, any individual will have an umbrella depending upon some kind of structure. So the girl will have umbrella only and only if the old man in previous day had an umbrella. So in this case, the girl will have 1. The old man will have umbrella only and only if the man in the previous day had umbrella. So which in this case is also 1. Then this man will have umbrella the next day only and only if the woman was having umbrella in the previous day. So we will put 1. And this woman will have umbrella only and only if exactly one of them has umbrella. One of them, exactly 1. Which in this case, this has 1 and this also has 1, which means we have 2. So this means the women will not be having the umbrella. And this specific procedure will be repeated till the time we will fill for some amount of numbers or values. So in the next day, so third day, once again, the girl will have if the old man has, so we'll put 1. The old man will have if the man had in the previous day, which is 1. Old man will have it 1 based on the women has it, but women had 0. So that is the reason we'll put 0 over here. I'll show you one specific example so that you will understand it better. And in this third, exactly as I mentioned, women will have umbrella if exactly one of them in the previous day, which is day number 2, will have umbrella. So which in this case would be again 0. So if you understood this specific concept, let me show you how exactly this LFSR concept also works. So what do you do is, I will be giving you some kind of a polynomial function, and in the end, you have to create a random number. So how do you generate that number? So let's play with initially 4-bit values. So let us imagine you have 1, 1, and 1. We will represent this as P, Q, R, and S. And here I will write output. Okay, so I am saying currently we will just create a pseudo-random number using the concept of LFSR, where there is a kind of a feedback mechanism and it is dependent on some previous state. And that is the reason it is termed as, it is dependent on linear feedback shift register. So what you will do is this value, which is represented by S, will come over here. That it becomes the output. The previous R becomes the new S. So you will come, make it over here. So this will shift over here. The previous Q will become the new R. So you will come over here. And the previous Q depends on the previous P. So that is the reason this will come over here. Okay, it's just shifted, 1, 1, 1 bit, shifted. The last bit becomes the output. And the new bit is somehow dependent on some other bit values, which in this case, let me represent this maybe with blue color. And I'm saying that let's depend on this R and S. So what exactly is the previous state of R and S? That will represent what would be the P value. And P value is the feedback over here. So P is dependent on an XOR operation. As I mentioned, this is exactly 1. And that's what happens in an XOR operation. So if it is 0, 0, the output is 0. 1, 0 is 1. 0, 1 is 1. And 1, 1 is 0. So exactly 1 means then only the output would be 1. So if the previous state value is 0, 1 or 1, 0, then only the new peak value would be 1. So here in this case, since the previous R and S value is 1 and 1, the output would be your 0. Okay, I'll make this pink back. So this will be 0. Now, once again, you will shift it. So this will come over here, 1. This will come over here. This will come over here. And this will come over here. So this will be your 0. Now, once again, previous R and S value, previous. So this was you started with this first, this is your second, and this is your third operation. So once again, 1, 1, the XOR operation will give you 0. Once again, you will apply a shifting operation and it is dependent on the previous value. So you will shift them. So this will come over here, 1, this will be 1, this would be 0, and this would be 0 over here. And 1, 1, once again, would give you 0. This is our fourth operation. And there is an output also, which is coming out over here. So once again, I'll repeat, this is 1, 0, 0, 0. This time it is 0 and 1, which means 0, 1 will give you 1. As I mentioned, we are following the XOR operation of R and S of the previous state. So previous state contained 0 and 1. So this is at fifth step. Fifth step, what exactly? Fourth step, R and S contains, and that you will apply an XOR operation, and that would give you the new P value. That's what we are doing. So here 0, 1 will give you 1 because it's an XOR of 0 and 1. Once again, we'll shift it. So this will be 0, 0, 1, 1, 0, 0 will give me our 0 value. So this is our sixth operation. Then we will have our 0, 0, 1, 0, 0, 0 will give me 0. Again, this is our seventh operation. Once again, I will repeat this particular process. And here, the output that we are getting, this output is actually the key. This output that we are getting, this is key. And we will repeat this operation continuously till we get the initial state. So if we get the initial state at some kind of operation, then in that case, it means that you have got your random number, but you do not know currently how random it is. And we will understand this once again, but you will be able to generate or get back this 111 at 2 to the power of n minus 1 operation. So where n is the number of bit. So 2 to the power of 4 minus 1. So 2 times 2, 4, 16. 16 minus 1, which means 15th iteration will give you back 1111. If you don't get back 111, then it means either you messed up the calculation or you have not got your random number. So I will try one more thing for 3 bits so that it becomes easier for you to understand. But any questions so far in understanding this mechanism that we just learned over here? Any questions? Okay, no questions. So let's do it for 3 bits. And I will tell you that you will be getting your output value as your value that you started with. So let's start with P, Q, and R this time. And let's start with 111. And there is also an output over here. And we should be getting at 2 to the power of 3 minus 1. So 8 minus 1. At 7th iteration, we should be able to get 111. If we did not get 111, then it means that we have some calculation that we have made it wrong. So here, this will come as 1, 1, 1. Once again, this particular part of on which bits that they are dependent would be provided to you. Once again, we will say that P is dependent on Q XOR R operation. So 0, 0 should give us 0, 1, 0 will give us 1, 0, 1 should give us 1, and 1, 1 should give us 0. So this is an XOR operation. So this is our first, this is our second. So 1, 1 will give me our 0 value. So this will come over here, 1, 1, 0. 1, 1 will again give me 0. This will come over here. This is 0, 0. 0, 1 will give me 1. This will come 0, 0, 1. 0, 0 will give me our 0. So this is 0, 1, 0. 1, 0 should give me 1. This is 1. 0 and 1. 0, 1 should give me 1. This comes 0, 1, 1, 1, 0 should give me 1. So you can see that I'm able to get back this 1, 1, 1. So this is our third, this is fourth, this is fifth, this is sixth, this is seventh. So after 7 operation, I'm able to get my original output, which is 1, 1, 1. And this output that we are getting, 1, 1, 1, 0, 0, 1, 0 is the key for your LFSR or for your stream cipher. Does it make sense, everyone? Good. So here, always, yes, you would require some practice, because I will be providing you the initial value, and I'll also provide you the polynomial function. So you can say this, for instance, this is x1, x2, and let's suppose x3. And I will say that maybe x1 is dependent on x2 XOR x3. Or other way, if there are 4, I will tell you that it is dependent on the 2 previous values. So if it is 4-bit, x1 is dependent on, let's suppose, x2 XOR and x4. And you have to look at the table, you have to look at the previous iteration, and you should come back with the original value. That is how you will know that this is what is the random key that you generated. But we still do not know that it is highly pseudo-random or not. We do not know that. And in order for us to know this, we have some kind of postulate which came into picture to know that whether this pseudo-random number that we have created is highly random, that nobody should be able to crack it. And for this, there came this Boehm's postulate. So here is that table. If you want to follow along with 4 bits, you should be able to. They just showed it for 12th iteration, but if you will run this for 15th iteration, and the 15th iteration, you should get back your original values, which was 0010 when you started. So if you want to practice at home, you can start with this 0010 as the initial input, and you should be able to get back your original 0010 by 15th iteration. If you do not get, then in that case, you have messed up your calculation. And the output is basically this output that comes out over here. So 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1 is your key value. So there are three important things that you should remember whenever you are working with a pseudo-random number, that it depends. It is your pseudo-random number is highly dependent on the seed value, which is the initial bits that you are starting with. So if you are starting with 111 versus if you are starting with 001 or 110, your output of your key would be totally random. So it is highly dependent on the seed value. The second important thing that is very important is the rules that you apply. So the rules is that if, for instance, if you are processing 4 bits and you can do x2 XOR x3, you can do, and this time, let's suppose it is x4, x3, x2, x1. Sorry, I've changed the numbering order. So x4 is dependent on x3 or x2, or it can be dependent on x1 or x2, or let us suppose it can be dependent on x4, x1, x2, and x3 as well. So that is the reason it is called as a linear feedback, because here, if you are starting with your 4 bits, which you are saying it as x4, x3, x2, and x1, you are applying a kind of flip-flop on this coefficient to get back your x4 value. So that is the reason it's a feedback based on the previous x1, x2, and x3 value to come up with the new bit value, which is x4. So these are the coefficients which trigger it. So C1, C2, and C3. So generally, your polynomial function, which you will write, would be C4 X4 XOR C3 X3 XOR C2 X2 XOR C1 X1. So if I am giving you a polynomial function fx and I say it is x3 and x2, which means that the most significant bit is basically dependent on these x3 and x3 and x2 values. So you will put the coefficient values this as 1 and 1. And the rest of these are 0, which means your final output is f of x, which is x3 XOR x2. Am I going too fast or you are able to understand?
We're all good. Worst case scenario, we can rewatch the Zoom recording.
Okay.
Thank you.
Okay. So yeah, so here this f of x is that linear feedback shift or a polynomial function which is dependent on these coefficient value which you are putting as 0 and 1. So maybe let me show this on the whiteboard. So as I mentioned, how likely are you to recommend whiteboard to a friend or a colleague? I think highly.
Just for asking, -10.
Okay, so here if you will see that if this is what I had mentioned, that you start with these PQRS values and you have your coefficient. Let's represent this as x1, x2, x3, and x4. There is a trigger for these flip-flops, which I'm representing this as C1, C2, C3, and C4. And as I mentioned, you apply a feedback to come over here to output your value. So these values come out. So x4 will come out, then x3 will come out, x2 will come out, then x1 will come out. And then the next bit, so once these will output x4, x3, x2, and x1, the new bit value that you are coming is dependent on the previous value. So let us suppose I'm saying that I don't want to depend on this, but I somehow want to depend on this C3 and C4 value. So I will say that this f of x that I'm creating, once again, this polynomial, it's linear in nature. That is the reason we have C1 x1, C2 x2, XOR C3 x3, XOR C4 x4. So this C coefficient could be either 0 or 1. So I'm saying in our case, this C3 and C4 is 1 and 1. This is 0, which means my polynomial function that I'm using, which is linear in nature and which gives a feedback, is dependent on x3 and x4 value. So f, this new bit value, which would be injected inside this register, this new register will contain the previous state values of x3 and x4. And that is the reason this LFSR technique came into picture, which is able to generate a stream of values which is dependent on the previous state, and it is linear in nature. That is the reason it is termed as that linear shift register. So the thing that I was saying over here, that this random number that you are generating in the end is dependent on the initial seed value. So this initial seed value could be some value that you are inserting. So this could be 111. Let's suppose we are processing 3 bits, 3 bits, x1, x2, and x3. So our initial bit value could be 111, or let's suppose I say it as 101, which means this output that you are getting would be totally different in both of these cases, because in the first example, you start with 111, and the other example, you are starting with 101. So the random number that you will generate would be totally different, because this will come out as 101 and this will come out as 111 if you will do it. And then it is also dependent on which previous state value that it is taking in to get the new bit value. So it could be dependent on just x2 value, or it could be dependent on x2 and x3 XOR value. If we are processing 4-bit, and if it is x1, x2, x3, and x4, it could be dependent on x2, x3, it could be x2, x4, or it could be x1, x2, x3, let's suppose, or it could be some other different combination. So that time also your output would be totally random. That is another important aspect of LFSR. The complexity depends upon the seed value, the rule that you are applying, and finally, your number of bits. So if the number of bits is 3 bits versus if the number of bits is 4 bits, the random number that you would be able to generate with 4 bit is 2 to the power of 4 minus 1. This one is 2 to the power of 3 minus 1. And if you are taking a 5-bit value, then in that case, it would be 2 to the power of 5 minus 1, which means the keys which are being generated would be totally random, as well as the size of the key would also be larger when you are taking larger bit values. So that is important concept of LFSR. Now, circling back to the final thing, this is a feedback, linear feedback shift register, that what exactly it is. It's a pseudo-random stream of binary for use in an XOR operation. But as I mentioned, the output that you are getting, somehow you also have to verify that the output that is being generated is actually highly pseudo-random or not. How can you identify that? And for that, people came up with this, or not people, there was this guy, Golem, who came up with this Golem's postulate. And this Golem's postulate, in order for you to understand this Golem's postulate, you should know these 3 important terms that I would be using. So the very first term is run. So run basically means we are understanding this Golem's postulate, which is used to identify the number is random or not, like highly random or not, which means that whether the malicious attacker could be able to crack this number easily or not. So if the bit values, if it is 3 bit, which means the output, the maximum number of bits that you can generate is like 7 bit, and then these 7 bits are being repeated. But if you are taking, for instance, 4 bits, then in that case, the maximum. So it can always, one thing that you should remember is that when I say that if you are starting with 3 bits, it should repeat after 7th bit, it is totally dependent on the initial bit values that you are taking, which means sometimes when you start with 101, you might be able to get this 101 at 5th iteration or 4th iteration. The maximum that you can get this repetition is 7. So if you are starting with some value, let's suppose 000, there could be a case that you are able to get the 000 at 3rd iteration too. So do not get confused. When I say that you should be able to get, which means that the maximum that you would be able to get your initial input seed value is 7 when the number of bits is 3, but you could be able to get the initial value even at the 3rd step. So that's what you should remember. So circling back to Golem's postulate, in order for us to understand what is Golem's postulate, there are 3 important things. One is run. So run basically means that if, for instance, I have this 101101 as the key that we created, runs means the consecutive set of either zeros or ones. So this is one run, this is another run, this is considered as 3rd run because you have 1 together. This is considered as 4th run, and this is considered as the 5th run. If I have 11110000, this is considered as 1 run, and this is considered as another run. I'll give you one more example. If we have 0011, 0011, This is one run, this is another run, this is third run, and this is fourth run. So it is defined as the consecutive set of zeros and ones. One thing that you should remember is run. The other important thing is autocorrelation function. And I think autocorrelation function I'll make you understand based on the example that I'll cover. But run, if you are able to understand, I think you should be good in understanding Goulam's postulate. So Goulam's postulate was that you can know that the number that you generated as your key is random if it satisfied three properties. One is 0, 1 balance. So let's suppose if you have 0, 0, 0, 1, 1, 1, 1, the first property says that calculate the number of runs. So here in this case is one run and this is another run. And you will check the number of bits. Sorry, I'm wrong over here. So if let's suppose I have the 0, 1, 1, 0, 1, 0, 1, you will calculate the number of ones and calculate the number of zeros. So here in this case, the number of ones is 4 and number of zeros is also 4. So 4 minus 4 gives you 0, which means this is not random because the number of ones minus your number of zeros should be less than equal to, or sorry, greater than equal to 1. If it is greater than equal to 1, then only your you have created your random number. Here in this case, this is also 4 minus 4. This will give you 0, which means it's not a random, highly random number. Let's pick another value, which is 1, 1, 1, 0, 0, 1. Let's suppose this. Yeah. So for in this case, it would be number of ones is 4 and number of zeros is 2. So 4 minus 2 gives you 2, which means this satisfies property number 1. Does it make sense what I'm trying to say? Is everyone getting or is it too much? Okay. 50-50. Okay. I'll cover just this example and then I can end the class and we might cover this example maybe in the next class. But let's understand these rules so that you can solve it in the next class. So in your next class when we will meet, I'll give you an example where you have to solve whether it satisfies Goulam's postulate or not. So the first important property, as I mentioned, is taking that random number that you have created and you will calculate the number of ones and number of zeros. And if the number of ones and zeros is greater than 1, then in that case, you have satisfied property number 1 for randomness. So here in this case, let's suppose your output of your LFSR that you got was 1, 1, 1, 0, 0, 1. Let's suppose this is the output that you are getting, or maybe 0, 0, 1, 0. So rule number 1, you will calculate the number of ones. So number of ones is 1, 2, 3, 4. And you will subtract with number of zeros, which is 3. And you will check whether this number is greater than equal to 1. If it is, then you have satisfied property number 1, which means it is kind of random, but we do not know it is highly pseudo-random or not. So for that, we will now go to rule number 2. So rule number 2 says, we will calculate the number of runs over here. So if you remember, the number of runs is consecutive sets of zeros and ones. So this is run 1, this is run 2, and this is run 3, and this is run 4. So second property basically says that if your random number that you generated, if the half of the runs have length 1, so the length of run R3 and R4 is 1, which means we have 2 runs out of 4 runs. So this is your first run, 2 run, 3 run, and 4 run. So 2 by 4, which means 1 by 2. Half the runs have length 1, which means this property is satisfied. If half of the runs have length 1, 1/4 have length 2, 1/8 have length 3, then in that case, your rule number 2 is satisfied. So you will first calculate the number of runs, then you will calculate the number of the length of runs, the number of runs with length 1. So here in this case, it is your 1, which is 2 over 4, because there are 4 runs. So that is the reason half the runs have length 1. 1/4 have length 2. So here in this case, we have only 1. So 1 over your 4 have length equals to 2. So this is your only run which has length 2, which means rule number 2 is also satisfied. Now we will go to rule number 3. Rule number 3 is slightly complicated. So that is the reason I'll cover it, but we'll cover the example next time in your class. So rule number 3 basically says you have to calculate the autocorrelation function for these bits that you are starting with, and you will perform an XOR operation. So I'll give you an example for that so that you understand. Autocorrelation function is, shouldn't the example string fail rule number 2, because R1 is length of 3, but takes, yeah, so it should basically fail for rule number 3, I guess, for rule number 2. Let's get back to the example that I was covering. Going back over here. Yeah. Okay. What was the original string that I took? Does anyone remember? 111 0010. Was it this one? Yeah. Okay. So here in this case, this is R1, this is R2, this is R3, and this is R4. So here in this case, we have 2 by 4 of length 1. So first is satisfied. The second one is your 1 by 4. So second one is also satisfied. For length 3, that should be 1/8, which is equivalent to, yeah, I guess for number 3, it will fail. But let us imagine in some case you have that each of these rules is also satisfied. So you go to rule number 3. I'm just giving you an example so that you understand autocorrelation function. But in this case, I think it doesn't satisfy property number 2. But let us imagine you got some number and rule number 2 is also satisfied. So in order to verify that it is highly pseudo-random, then in that case, you will follow this autocorrelation function. So let me show that. So autocorrelation function says, so let us suppose your bit that you are starting is, or your initial key that you generated is 0, 0, 0, 1, 0, 1, 0. Let us imagine this. Or let's pick the same example, 1110010. This was your original key bit value. Autocorrelation function says that you will shift 111 bit. So here in this case, you are starting with 1110010. In this case, I will not shift it at all, but I will just XOR S with S because I'm not shifting. So if I'll XOR the bits with the same value, you will get 0000000. So that is your first S. Then S, the shifting is 0. You take your S and you apply an XOR with a shift operation. So let us suppose this was S1. And in this case, I'm not applying any shift. So let us represent this as S2. You will XOR it together. S1 XOR X2. And you will write the number of ones that you are getting in the resultant output. So the number of ones is 0. And the number of bits is 7. 1, 2, 3, 4, 5, 6, 7. So that is your autocorrelation or coefficient autocorrelation function when there is no shifting being done. Now let us imagine you shift this value that you originally started with 1 bit. So if it is 1110010, which I'm representing this by S1, let's shift it 1 bit. 1 bit. So this will become 110010, and this one will come over here. So you're shifting it only one time. So let's represent this as S2. You will XOR it together and you will get the resultant output. So here in this case, this will give you 1. This will give you 1, 1, 0, 1, 0, 0. So here the number of bits that you are getting is 4. Number of ones is 4 over the total number of bits, which is 7. Now let us do for one more shifting. So this was for shift 0. Let's do it for, I did it for shift 1 when we shifted it one time. And let's do for shift 2. So for shift 2, once again, your S1 would be your original value, which is 1110010. This time you will shift it twice. So this would be 100, 10, and 11. You shifted it two bits together. You will once again apply an XOR operation. So this time it is 100, 1110. Once again, the output coefficient value is number of ones, which is 4 over 7. So this is 4 over 7. So autocorrelation function or Goulam's postulate, according to rule number 3, says that if you will take your original key and you will shift it multiple times, like 0 bit, 1 bit, 2 bit, 3 bit, 4 bit, the resultant should always give you 2 values, 2 unique values. So in our case, we got 0 over 7 and we got 4 over 7. If we apply shift 3, if we apply shift 4, I should be getting 4 by 7, 4 by 7, 4 by 7. If I do not, then in that case, I do not have a pseudo-random number. If I get it, then it means third property is also satisfied and we have achieved or we have got a perfect pseudo-random number to be processed to do your stream cipher calculation. Does it make sense? Does it make sense or no? Kind of? Okay. So let's do one thing. I think I covered a lot of things, but this was Stream Cipher. So Stream Cipher comprises of what we covered was we started with AES, we did our linear feedback shift register, which is used for creation of a key, which is pseudo-random number. But in order to test that number that you are generating using that LFSR is highly pseudo-random, is dependent on if it follows Golom's postulate, and Golom's postulates has 3 rules. And if it satisfied 3 of the rules, then in that case, this random number that you came up is highly pseudo-random, which means you can use that number for stream cipher. So this value, so let us suppose if we are getting 1110010, this is highly pseudo-random, which means for an attacker to know this key would be very hard. And that is the reason this Golom's postulate verifies that whether this numbers that you are generating is actually random or not, pseudo-random or not. Okay, so in the next class, what I'll do is I'll give you one example that I want you to solve in the class. You will verify it for, I think in your quiz, I have that specific question. We can do that specific question in the class, or we can just do another question in the class so that you can verify whether the number that you have generated is pseudo-random or not using this Golom's postulate. So with this, I think I'll end the class. In the next class, we'll cover that example. I'll give you one more, I think DES, AES Stream Cipher is covered. I'm thinking because we have a couple of classes, then you have your, I think we can cover RSA algorithm and your Diffie-Hellman key. Diffie-Hellman key, we will cover that, which is the underlying phenomena for RSA. So we'll cover that, and I think that should be all for your exam, for your final exam. Okay, so with this, I'll end the class. If you have any question, I'm here. Otherwise, I hope everyone have a good weekend, and we'll meet next week. Thank you, everyone. Take care.
You as well. Bye.
Bye.
Thank you.
Bye.